Okay, if we have a first order equation, then we know how to transform y prime now. It's just y of 0 and hopefully negative y of 0, and hopefully we have an initial condition that gives us y of 0, plus s times the Laplace transform of the y function. In a linear equation, the whole left-hand side, if it's written in traditional form, is then going to be easy to express as an algebraic equation with the unknown being the Laplace transform of your y function. Right-hand side could be any other function as long as you can Laplace transform it. Then you transform the whole equation into an algebraic equation and you solve it using algebra, usually relying on a lot of partial fractions. What if you had a second order equation? Well, then you would have to be able to do Laplace transform of the second derivative. Well, it's really pretty easy to do that, and the higher derivatives are equally easy. Let's just see what happens when you go to the second derivative. Laplace transform of f double prime is, of course, the integral from 0 to infinity of f double prime of t e to the negative ts dt. And I'm not going to write out the steps of the integration by parts because they're really obvious. Among other things, we're going to let dv equal f double prime of t dt, so v is the antiderivative of f double prime, so v is f prime. And I'll just put an etc. here because I want to have a little more board space down here. So this equals f prime of t e to the negative ts. And again, you can write out the details. They're simple enough. And I think I'm getting them right. And then it's going to be plus s times the Laplace transform of f prime. And again, I'm not going to write out the details. I want you to do that. Write out the details and convince yourself of this. But, what's the Laplace transform of f prime? Well, it's this. So what you get is, first of all, you get f prime of 0. Now, your condition on f is that f and all its derivatives are such that all of them grow more slowly than e to the negative ts, so the integral, or the limit at infinity, is 0. So don't try to apply this to like an e to the x squared function. It's not going to work. Okay? But anyhow, you get f prime of 0 plus s times this derivative. That's negative f prime of 0. I'll never get this right. Okay, s times negative f of 0 plus s times Laplace transform of f. Of course, you use the distributive law, so you're going to get a negative f prime of 0 minus an s f of 0. You're going to put an s in front of this, in other words. And then you're going to end up with s times s, which is s squared, times the Laplace transform of f. Now you're going to be doing algebra with this, so you're getting into quadratic expressions and so forth, and there's no limit to how nasty those expressions can get, but as long as you can factor what you have, you're going to get good solutions. Of course, not everything can be factored. And that's all I'm going to say about that. I mean, I could write out this would be negative f prime of 0 minus s f of 0 plus s squared L of f. The main thing to understand is that if you have initial conditions that tell you f prime of 0 and f of 0, then this just reduces to simple algebra on L of f. and you can transform your equation into an equation where the unknown is the Laplace transform. The equation will typically be then Laplace transform is going to reduce to a rational function that you can then break down using partial fractions. Okay, that's typical. It won't happen in every case. But in the cases that we're going to see in this course, that's what pretty much happens. Okay, so now let's go on and continue the adventure by solving an equation, and you're going to see how neat this can be.